Hey everybody, today I'd like to talk about spheres, and specifically one theorem about spheres that I find quite interesting. It's called the Borsuk-Ulam theorem, if you haven't heard of it before. And it says the following. There are always two antipodal points on Earth's surface with the same temperature and air pressure. So this is a claim that will generalize to all spheres, and you can sort of use any two variables. I like to apply it to Earth to make it more understandable and more interesting. There's nothing special about temperature and air pressure. These are just the ones that I picked. Temperature and air pressure. Antipodal points just refers to 2 points that are completely opposite on the sphere or on the Earth. So for example, the North Pole and the South Pole are antipodal points. Or this point here and whatever's behind the Earth, like in here region, I guess. They're gonna be antipodal as well. Cool, so one key assumption we're going to make, and this is going to affect the whole proof, is that temperature and air pressure are continuous. Now this is important. What I mean by continuous is that if you walk a little bit, they're going to change a little bit. But if you walk a lot, they can change a lot. So if I have a line here, and there are temperatures all across the line, and I want to graph them, let's say the temperature here is 4 degrees Celsius, and this is 12 degrees Celsius, I'm going to have some kind of chart that maps the temperature as I walk across the line. And the idea of being continuous just means that this chart, as I draw it, I can't take my pen off the page. So this is fine, temperature grows, it might go really fast, it might stay a bit and go down. This is all continuous. But the second I have something like this where it stops and now it just jumps temperatures sort of instantly, this breaks the continuous property. So we're just saying that this is true of temperature and air pressure, which actually is the case. So it shouldn't violate anything in our theorem. So as always on this channel, something I like to do is to break the problem down into a smaller problem or a more simple problem. Spheres are going to be a three-dimensional object, obviously, so let's try this in a two-dimensional variant. I'm going to try and show a very similar claim holds on a ring. And I say ring and not circle because we're actually only interested in the outside of the ring, the circumference, in the same way that on the sphere, we're only interested in the surface area, or the surface space, I should say. I want to try and prove that two opposite points on a ring, there are always going to be two opposite points on a ring that have the same temperature. Again, I can pick any variable I want. I'm just going to choose temperature. And again, we're assuming that temperature is continuous. So let's try and prove it. Well, let's pick two random points. And let's call them P1 and P2. Now, I need some sort of elegant way to speak about the temperatures at P1 and P2. So let's create some kind of function. I'm going to call the function T. And it's going to take in a point, I suppose, from the set of points. And then it's going to output, I guess, a real number. This is going to be the temperature. So for an example, we might say that T of P1 equals 15.4, which means that it's 15.2, sorry, which means that it's 15.2 degrees at P1. So this is the function we're going to use. It's going to be called T. Now, we have two cases here with these 2 points that I picked, P1 and P2. And let's just say that this is the very northmost or the upmost point and this is the lowest point. Now, it might be the case that T of P1 equals T of P2, which is brilliant. And if that's true, we're done. Right? We've proven that there's two points that are opposite that have the same temperature. Now, temperature isn't just going to be numbers like, 13, 14, 15, whatever. They're going to have a decimal component as well. So the odds that they're both the exact same are going to be really low. So that's case one. But case one probably isn't going to happen. Now, case two is that they are not equal, right? Which is more likely to be the case. It's probably going to be the case that the two random points I pick won't have the same temperature. So what happens if they're not the same temperature? Well, let's pick one arbitrarily and say that it's got a larger temperature than the other. I'm just going to say, let it be the case that the temperature at P1 is larger than the temperature at P2. And you might be wondering, well, you can't just say that, because what if P2 has a larger temperature? If it does, let's just flip the problem around on this axis here, and you know, flip everything around, and now P1 becomes P2, and now P2 becomes P1. Hopefully you can see that because this puzzle was symmetrical, it doesn't actually really matter. We don't lose any generality when I just nominate P1 as the thing with the higher temperature. So we have that P1 has a higher temperature than P2. So let's just get some more definitions in here. Let's just say, let's let X equal the temperature at P2. And because the temperature at P1 is larger, let's let X plus K be the temperature at P1. And all that's important here is that we have that K is going to be some real number that's strictly positive. It's going to be a positive real number. So this is the temperature at P2 is X for any X, doesn't matter. And the temperature at P1 is going to be X plus some positive number K. Just means it's larger. So with that out of the way, let's draw a little graph. That graphs the temperatures. And we're just going to be at one point on the graph right now. This is going to be, let's say that this point in the graph is going to be X plus K. And this point in the graph is going to be X. And we know that T at P1, now P1 I'll use a red thing. It's going to start here. And T at P2, which I'll use blue for, is going to start here. Cool, alright. Now here's what I want to consider doing. I want to imagine moving P1 clockwise around my ring and moving P2 clockwise around my ring, but keeping them at opposites from each other. So they're moving at the same speed. So let's imagine we have some kind of axle here and it's rotating along the center point, so it's rotating clockwise. Like we have a sort of a hinge thing here, right? It's pivoting around. The line's moving at the same point. So point 1 and point 2, they're constantly changing, but they're always opposite from each other. So they're always going to be having this property where they're, I guess, antipodal. Now, once we move them around 180 degrees, what's going to happen? Well, P1 is going to end up where P2 was, and P2 is going to end up where P1 was, which means that the temperature at P1 is going to end up down here. And the temperature of P2 is going to end up here. And now all we have to do is consider some of the ways that this graph can look. So my x-axis is going to be kind of like my rotation. So this is my 0 degree rotation. This is my full 180 degree. So the value of P1 is going to start at X plus K and it's going to move, might go up, might go down. It doesn't really matter. But it is going to end at some point here, and it has to end exactly here. Now you can probably see where I'm going with this. Now let's consider the trace of P2. And again, it's completely general. It doesn't really matter what it actually happens specifically, but it has to end up in that top right corner. And you're going to notice quite quickly that no matter what I do here, my lines have to intersect. And that's no coincidence. One line had to go from here to here, one had to go from here to here. They're forced to cross over at some point. And at that exact point where they crossed over, point 1 and point 2 were still opposites, and they had the exact same temperature. So we can say with full certainty that at this point, wherever it happens to be, T of P1 equals T of P2. And P1 and P2 are opposites. So we've proven it for a more simple case. We've proven that this is true on a ring for one continuous variable, temperature. Now we're going to try and extract it to a sphere with two continuous variables, temperature and air pressure. Cool, so I'm going to rubble this out. and we'll start talking about that. The Earth is just going to be a bunch of rings at the end of the day. This is one of my rings here. And if I want to rotate it a tiny bit, like this, it's going to be hard with Google Paint with this one because it's a lot of 3D stuff. This is another ring. And I can actually fit infinite rings in here. And they go all the way around, I should say. They wrap around. So they're going behind this sphere as well. You just can't see it. It's going to be another ring here. Maybe it goes through like this. There's an infinite amount of rings. And one thing that we know is that on any one ring, there exist two opposite points with the same temperature. We've just proven that to be the case. Let's actually just use the rings that are on this image. So for example, like this ring here that just goes straight down, we're just going to use these. Somewhere on this orange ring that cuts the sphere into two is going to be a point with the same temperature and air pressure. Sorry, with the same temperature. Let's just nominate a point then and say it's here. Doesn't actually matter where it is. And now we're going to nudge the ring ever so slightly. Now we're going to consider this ring. And now on this ring, there's going to be a point with the same temperature. And because I can pick arbitrarily how much I want to nudge these rings by, in calculus I would say that this little red gap here is going to be dx. And I can consider what happens as dx approaches 0. This is a limiting idea. We won't get into that now, but the idea is that the smaller I nudge these rings, the closer together this green dot will get to whatever green dot I get on this side. And if they get arbitrarily close, the green dots are going to get arbitrarily close. So let's say the next green dot ends up here. And the next green dot might nudge a little bit here, and then here. And it doesn't matter, but this green dot is going to be continuous, and it's going to wrap around my sphere. It might go up a bit. This goes all the way around the back. And this is for every possible orange ring I can make. So this is basically a set of infinite points. And those points are all continuous. Now here's what I can do. Because these green dots all basically form a border, I can just call them in like this and trace. Oh, I'm not trying them in. Trace them. This is going to go behind this. This last bit is sort of behind the sphere. And what we'll find is that because we're talking about opposite points, the ring is going to be symmetrical. So, well, not symmetrical. The ring is going to have this property where for any point on the ring, its antipodal point will also be on the ring. And it's because that's how I measured them. It's because with every orange ring, I was taking a pair of antipodal points. They were opposite from each other, which means that for any point on my purple ring, its opposite point will also be on the ring. So now I have a purple thing. It's not quite a ring anymore, but it looks a bit fuzzy, but it is still true that for every point, the opposite point is on the ring. So these 2 points are opposites. And maybe this point and this point are also opposites. So there's no reason why I can't run the exact same argument once again. I'm going to pick an arbitrary point and its antipodal point. I'm going to label this one 0.1 and this one 0.2, and I'm going to make the exact same case where my temperatures are going to have to cross as I move these points clockwise 180 degrees. Now remember, this purple line defines the set of all points that have the same temperature. So on the sphere, there are going to be infinite sets of antipodal points with the same temperature. And when I apply this exact same calculation to that set of points themselves, there's going to be one intersection here on a second variable, and that's going to be air pressure. So now what you've shown is that on this purple ring, there's going to be at least one pair of opposite points that have the same air pressure, and these points already have the same temperature, and that proves a theorem. So there must be at least 2 opposite points on this sphere that have the same temperature and air pressure. The interesting thing about this fact is that it actually is true in real life, and it's got real life, I won't say implications, but we can think about this as true. So one important thing to say is that obviously temperatures change all the time in the real world. So even though there always at any instant in time exists 2 points with this property, those 2 points are always going to change and at rapid speed. So right now, point 1 might be in Africa, and in 2 seconds it might be in Sweden. We can think of these points as constantly moving around because temperature is always changing. This fact exists at every snapshot in time. But when you consider a temporal dimension, these points are going to wiggle around. And you're never going to actually find what these points are in real life, because by the time you've measured them, they've changed. We've shown that this is true for a sphere. So we've shown that it's true on a ring with one continuous variable. We've shown that it's true on a sphere with 2 continuous variables. So a very reasonable thing to ask now would be, what about a hypersphere? Hypersphere with 3 continuous variables. So maybe we can go temperature, air pressure, and then the strength of the wind, or maybe the volume, like maybe the sound volume from that taken from that area. I don't know, anything continuous, it shouldn't really matter. But yeah, can I abstract it more? So on a 4D sphere, can I have 3 variables? On a 5D sphere, could I find 2 opposite points with 4 variables? And you can actually go in the other direction as well, and I'll show what I mean. So we've shown in this video that on a 2D sphere, which is basically my ring, we can have this is my number of variables, and this is my dimension. So 2D, I can find opposite points with 1 continuous variable. 3D, I can find 2 opposite points with 2 continuous variables. And yes, this pattern actually does continue. And I'm not going to prove it, but the proof is going to be basically the exact same. I'm going to be taking a 4-dimensional sphere and lining up a ring of these yellow points, and then doing a 3rd variable on those. So in general, in an n-dimensional space, on the surface of an n-dimensional hypersphere, you can find 2 antipodal points that have n-1 continuous variables. Now if we go back up in the other direction, we can say a 1-dimensional space, there exists 2 opposite points with 0 continuous variables. This one's a bit more hard to wrap your head around because a 1-dimensional space is just going to be a point. But because it's just a point, that is kind of true. They don't really have any continuous variables. There's no space here for a variable to even be continuous. It's probably the best way to think about it, but I think it's clearly more interesting to go in this direction. But yeah, the 3D case is the one I chose to focus on because it maps onto our Earth well. But yeah, that's the end of the video. Thanks for watching, guys. Cheers.